Hello everyone. Before starting the problem series, okay, we will have a look at the MOSFET current equation. Just a quick revision. Okay, so this is NMOS, this is the PMOS. You know the symbol. Gate. This is gate. This is drain. This is source. Drain is at higher potential. Source is at lower potential. The direction of current is from drain to source. This is that is sure. That is drain. The source is at higher potential. The direction of current is from source to drain. Okay. uh, what you need to remember is that one with the this arrow will be always at source. This arrow will be always at source, and in PMOS source will be at higher potential. Okay, and in NMOS drain will be at higher potential and source will be at lower potential, and in this one drain will be at lower potential. This is gate. This is gate. ID current will be from drain to source in NMOS and from in PMOS from source to drain. When VGS is less than VT, it will be in cutoff. When we are going from NMOS to PMOS, what you need to do? Just replace S and G. Okay. When VSG is less than mode of VTP, then it will be in cutoff because VTP is negative in the sun. So we have to take mode of VTP. And when VGS is greater than VT and this VGS is greater than VT, it means the NMOS is on. But the other condition is that VDS is less than VT. Okay, when VDS is less than VGS minus VT, that means it will be in linear region. Okay, in linear region, what is the current equation? That is mu n COX W by L VGS minus VT into VDS minus VDS square by 2. Okay, second, in this one just replace VSG. VGS is VSG. If VSG is greater than mode of VTP and VSD is less than VSG minus mode of VTP, then it will be in linear region. Okay, we are not writing VDS and VGS here. For PMOS we are writing VSG because one which is that higher potential we are taking that. Okay, so it will be in linear region and the current equation would be mu P COX W by L VSG minus mode of VTP into VSD minus VSD square by 2. Okay. Third point, when VGS is greater than VT and VDS is greater than VGS minus VT, then it will be in saturation. Okay, current ID would be mu n COX W by 2L greater than or equals to VGS minus VT whole square. Here VGS is greater not VGS, it would be VSG. VSG is greater than mode of VTP and VSD is greater than or equals to VSG minus mode of VTP. Then it will be in saturation region. Then your ID would be mu P COX W by 2L VSG minus mode of VTP whole square. Everything related to this one we have seen in the what MOSFET physics. MOS physics in that we have seen everything. What else? Yeah, here the drain current is equals to source current, right? And fourth point is that the gate current is 0 because of that oxide. We have oxide here, right? We have oxide here. The gate current is 0 because the oxide doesn't allow the negative charge to pass or the positive charge to pass. So the gate current is 0. Okay. Here gate current is 0. Or fifth point, like this drain current and source current are equal, right? I'm not writing this point. Drain current and source current are equal. There is no term as a source current. They call it drain current only. But whatever the current is flowing, that is flowing in the complete circuit. From up to down, the complete current is being flown, right? From up to down, the complete current is being flown. And one more point here, drain at higher potential. Drain at higher potential. And here, source at higher potential. Source at higher potential. So that's it. Okay, so this is the this is just a quick revision that you need to know. Okay, so now we will see numerical problems. Okay, not numerical problems, we will see interview questions. Okay, hello everyone. So now let us see the first interview question. So these kind of questions are very oftenly asked. Okay, so now, and I don't think there is any other source available. These questions are from Razavi notebook, Razavi book. Okay, Razavi, Rajavi's book. So on YouTube, I don't think any kind of lectures are available for these kind of questions. So yeah, what you need to do, Vx is varying from 0 to 3 volt. Okay, we have to take threshold voltage to be equals to 0.7, and when we consider PMOS, you will take threshold voltage to minus 0.7. Then you have to plot Ix versus Vx and Gm versus Vx. Okay, so first your Vx is varying from 0 to 3 volt. So what we will do, we will write VDS. Okay, this is at 3 volt, and this Vx is varying from 0 to 3 volt. But so what does that mean? It can't go above 3 volt. Okay, Vx can't go above 3 volt, so that means it will always be lesser than 3 volt. That means it will always be drain, it will always be source, and this will always be gate. You can point drain, source and gate now. Okay, we will take some questions where you can't point those, we will see that. But here, that upper one will be drain, this will be gate, and this will be source. Okay, so what is your VDS here? VDS is, this is the proper method of solving these kind of questions. Just don't be in any hurry. Okay, just solve it like this, calmly solve it, you will be able to solve. Just write these point, what is VGS, because these point you need, right? What is VGS? VGS is 3 minus Vx only. Okay, what is VT? VT is 0.7 volts. 0.7 you can write, or volt we can write. From here you can calculate V overdrive. This factor VGS minus VT, we call it V overdrive. Okay, we call it V overdrive. This VGS minus VT, we call it V overdrive sometimes. Okay, that is 2.3 minus Vx. Here your VDS is always greater than V overdrive, right? Here your VDS is 3 minus Vx, and your V overdrive 2.3 minus Vx. That will always be greater than, VDS will always be greater than V overdrive, right? So that means MOSFET always remains in saturation. Always remains in saturation, right? So what will be the current equation? What will be Ix? Ix will be mu n Cox W by 2L. What is VGS? What is VGS minus VT? VGS minus VT, V overdrive, right? 2.3 minus Vx whole square. 2.3 minus Vx whole square. I can write it at some k, some constant k. 2.3 minus Vx whole square. This is what your Ix. Let us draw it here. You are plotting Ix versus Vx. One more thing you will see, when Vx is greater than 2.3 volt. Okay, one point we can note down here is that when Vx is greater than 2.3 volt, let us assume Vx, this is 2.4 volt. Here you have 3 volts. What is your VGS now? 0.6. That is less than VT. That means your transistor is off, right? So whenever, so if Vx is crossing 2.3, your transistor gets off. Your MOSFET gets off. MOSFET off. That means your ID is 0 ampere. Okay. So and one more thing you can see here is that you can draw this graph, or intuitively you can see, if you are increasing Vx, your VGS value is getting decreased. If your VGS is getting decreased, then VGS minus VT value is getting decreased. That means your current is getting decreased. if you are increasing Vx, that means source potential is getting increased. That means VGS is getting decreased. Gate to source potential is getting decreased. If gate to source potential is getting decreased, that means the current equation mu n CoX Wi 2L VGS minus VT, that is getting decreased. So the current is getting decreased. So it will start from high and then decay down. And at what point it will become 0? That point will be 2.3 volt. And after that it will always be 0. Let us assume we have a 3 volt here. So after 2.3 it will always be 0. And what is the region here? The region here is saturation. It is always in saturation. Okay. Now we need to calculate GM. What is GM? Del ID upon del VGS. Okay. What is your ID? IX. Del IX upon del. What is your VGS? 3 minus Vx. 3 minus Vx. Right? So what will be GM? Del Ix upon del Vx minus sign. Because this is constant. Right? 3 is constant. So del Ix upon what is the partial differentiation of 3 minus Vx? It would be minus del Vx, right? So your GM would be minus del Ix upon del Vx. That is your GM. So from here you can calculate GM would be some constant k dash 2.3 minus Vx, right? This minus sign will be there. If you multiply it with Vx, minus sign will also be there. Minus minus will cancel out. So GM would be 2.3 minus Vx. So simply at 0 it will be maximum and then it will decay down. This is your GM, this is your Vx. This will be maximum and at 2.3 it will go to 0 and after that it will remain at 0 only. Okay. So this is the complete analysis. Okay. That was an easy question. So next question will not be that much easy. That question was on easier side. So we will see more analytical question where you need to do more intuitive analysis. So I hope you have understood this one. Just write VDS, VGS, VT. Then you will see if it is in saturation or linear region. According to that, you can write the equation and just draw the graph. And then you can find the value of GM as well. And by that, you draw the graph. Okay. GM is always del ID upon del VGS. VGS we simply wrote and then you can get the graph. Okay. Now we will see one more question. Okay. So in the next video, we will see that other question. Hello everyone. Now we will see this question where you have to plot Ix versus Vx and GM versus Vx. And your Vx is varying from 0 to 3 volt and Vt is varying from 0 to 0. Vt is 0.7 volt. The conditions are same. The question is same. Just the circuit is different. Okay. Now I will ask you one question. Okay. If Vx is 0.2 volt, so what will be the current? It will be 0, it will be positive, it will be negative. What is the answer? Just pause the video, think about it. If Vx is 0.2 volt, what is the answer? It will be 0, but this answer is wrong. It will be negative. Why so? I told you there is nothing like source, drain and gate. Okay, I need to put the charger. Yeah, so what I was saying is that there is nothing like source, drain and gate. The MOSFET is a symmetric structure, right? If you see the structure, MOSFET is symmetric, right? Here source, here drain, n plus n plus. If you cut it from mid, you will find two symmetric structures, right? So anyone can work as drain, anyone can work as source. But in case of NMOS, drain is at higher potential, and in case of PMOS, source is at higher potential. So if Vx is less than 1 volt, so when Vx is less than 1 volt, which will be at higher potential? This one. So this one will act as drain. Okay. So let us draw the circuit again. This 1 volt will be the drain. This is gate 1.9 volt, and this will be the source. Okay. The current is from drain to source. This will be drain. This will be source. And the current will be from drain to source. That will be equals to minus Ix. Opposite current is flowing from drain to source. Current will be from drain to source. Okay, when Vx is less than 1 volt, then the lower potential becomes source and higher potential becomes drain. Okay, now here you see, what you see is that, what is your VGS? What is your VGS? That is 1.9 minus Vx. Right? What is your VDS? That is 1 minus Vx. What is your V overdrive? VGS minus VT, it would be 1.2 minus Vx. So here your VDS is always VGS minus VT. Am I doing it all right? Yeah, VGS minus. So here your VDS is always less than V overdrive. That means it will be in linear region. What did you do? You just made the circuit. You just said that this lower one is acting as a drain. This one is acting as a source, because it is at lower potential. This is at higher potential. So this is drain. This is source. The current is from drain to source. ID equals to minus Ix, and this one. So here you wrote VGS. What is VGS? VGS is 1.9 minus Vx. What is VDS? That is 1 minus Vx. What is V overdrive? V overdrive is VGS minus VT. That is 1.2 minus Vx. And here your VDS is less than V overdrive. That means it is in linear region. So what is the current equation? It will be ID equals to minus Ix. So instead of writing ID, I will simply write Ix equals to minus sign, some constant. Okay. VGS minus VT. VGS minus VT. That means this one, into VDS minus VDS whole square by 2. So this is simply the graph, right? So for Vx less than 1 volt, we are just making the graph. And for Vx less than 1 volt, will the MOSFET will be on? Yeah, MOSFET will always be on for Vx less than 1 volt, right? Because for Vx less than 1 volt, VGS will never go below 0.7. For, we can write it here, for Vx less than 1 volt, VGS is always greater than VT. That means your Vx minus 1.9 is, sorry, 1.9 minus Vx. 1.9 minus Vx is always greater than 0.7, right? For Vx less than 1 volt, Vg. So that means the MOSFET will never be turned off. So if we just draw the characteristics just for Vx less than 1, Ix and Vx. So what do you see here is that just don't draw the circuit by, just don't draw the characteristics by this equation. What you will see, if you increase the Vx, your VDS value is getting decreased. If you increase the Vx, your VDS value is getting decreased, along with your VGS value is also getting decreased. So your current should decrease, but your current is getting decreased in negative direction. We are plotting Ix. We are taking x-axis as yeah, we are plotting Ix. Y-axis is at Ix. Okay, we are taking Y-axis as Ix. So Ix is in this direction, but our current is getting flown in opposite direction. So we are having minus Ix current. So your minus Ix current is getting decreased. Means your current is getting decreased in negative direction, that means it is getting increased in positive direction. Do you get it? Your magnitude of current is getting decreased. You understand that? If you increase Vx, Vds will decrease, Vgs will decrease. That means your magnitude of current is getting decreased. If but the magnitude is getting decreased, but the current is negative. So let us assume initially you had this current. Initially you had -4 current. Now your magnitude of current is getting decreased. So it will go to -3. Magnitude of current is getting decreased. -4, -3. So if this is -4, this will be -3 and it will go like this. Linear it will be. In linear region it will be. The graph will not be linear. The region of operation of MOS is linear, right? So it will go something like this. This is Vx equals to 1 volt. Till this point, everything is clear, right? Just think about it. Okay. So it is starting from here and it goes like this. Okay. Now for Vx greater than 1 volt, greater than or equals to 1 volt. Now what will happen is this circuit will come again, right? For Vx greater than 1 volt, right? Yeah. And this is Ix. What is your Vds now? Vx minus 1. What is your Vgs now? 0.9. What is your V overdrive? Vgs minus Vt, that will be equals to 0.2 volt. Okay. What is your Vds? Vx minus 1 volt, right? Because now this is working as drain. This is working as drain because now this is at higher potential. So this is drain, this is source, and undoubtedly this is gate only. Okay. Yeah. So this is the condition now. Now what is your V overdrive? V overdrive is Vx minus V overdrive is 0.2. So for Vds less than 0.2, that means Vx minus 1 less than 0.2, that means your Vx less than 1.2. This will be linear region, right? When Vds is, what is Vds? Vds is Vx minus 1, that is less than 0.2. So your Vx will be less than 1.2. So for Vx less than 1.2, we will have linear region. So what will be the current? Id will be some constant Vgs minus Vt into Vds minus Vds whole square by 2. So if you draw the curve, Ix versus Vx for Vx less than 1.2. So this is the linear region. If you increase the Vx value, your Vds will increase. If your Vds, this is constant value, right? This is constant. Your Vgs minus Vt is constant now. If you increase the Vx value, your Vds will increase. If your Vds will increase, your current will increase, right? So from here you have already seen that your current is something like this. After that it will also increase. So this is 1.2 volt. This is 1 volt. Okay. So here your current is getting increased only. From 0 to this is getting increased. Okay. Now what do we see? After Vx greater than 1.2. Okay. When Vx is greater than 1.2 volt. Now when Vx is greater than 1.2 volt, what happens? This will go in saturation region, right? And your Vgs minus Vt is constant. Your Vgs minus Vt is constant. So what will be the current? Current Ix would be some constant. Vgs minus Vt is 0.2, right? This is 0.2. So the current becomes constant. Okay. I'm just plotting the graph. It starts like this. Then after that it becomes constant. this is 1.2 volt, this is 1 volt, this is Ix, this is Vx, okay. This is 0 volt, right? So this is the curve, okay. No one will ask you the magnet, no one will ask you the how much current is there, just the curvature. This is the nature of curve. In this region it is acting as a in linear, after that saturation. Here the saturation doesn't mean the current has to be constant, right? Because Vx was changing. In previous question, what do we saw is that here we had saturation but the current was getting decreased, right? Here we had saturation but the current was getting decreased because the current was getting dependent on Vx. Here this quantity was not constant. So if this quantity is not constant, the current will decrease. Okay, you just don't need to think that, oh, this is saturation region, so I will make the current constant. You need to see if overdrive voltage is dependent on the Vx, depending on the varying element, okay, varying voltage. So here Vgs was depending on the varying voltage. Here your Vgs was varying. So doesn't really mean that it will always be constant. For every Vx value it is constant. For every Vx between 0 to 2.3 volt it is in saturation region, okay. And in this one you saw the 3 region. We will just revise it once again. Also we have to see GM as well, okay. So what do we saw here is that initially yeah, when Vx was less than 1 volt it got interchanged. Upper one became source, lower one became drain, because this was at higher potential, so it became drain, okay. Now VGS was in this one, VGS was VGS was 1.9 minus Vx, your VDS was 1 minus Vx, your V overdrive was VGS minus VT, so 1.2 minus Vx. So here your VDS is less than V overdrive, right? VDS is less than V overdrive, so it will always be in linear region. So this is Ix, okay. Yeah, so what we had seen is that, so in this condition the current is the MOSFET is in saturation in linear region, and this is your current. If you talk about GM, in the next page we will talking about GM. We should have talked about that with current only, but I forgot that, okay. Talking about GM. So taking the first condition, when Vx is less than 1, this one, when Vx is less than 1, so what is our this will be in linear region, right? This is in linear region. So our GM is del ID upon del VGS. What is your ID? ID is minus Ix. What is VGS? VGS is 1.9 minus Vx. 1.9 minus Vx. So it would be del Ix upon del Vx. Okay. So simply the slope. So it will be here. What will be the slope? A straight line. Okay. Or there is another way of looking at it. Is there any other way? Because it will be simply del ID upon del VGS, and you can simply apply the formula as well. You can apply the formula as well. If I apply the formula, by formula we get mu n CXW by L into VDS. VDS is 1 minus Vx. Yeah, okay. So this is not a correct method, I guess. Yeah, this will simply be slow. This will simply be the slow. But what also you can do is that for Vx less than 1, you know the formula of GM, right? I have already told the concept of GM. So MOS is in. If you do by this concept, you will do many mistakes. So you just need to see the region of operation. MOS is in linear region. Okay. For linear region, what is the formula of GM? for linear region, not for saturation. Gm is mu n cox w by L VDS, right? It is VDS because del ID upon del VGS we need to do. This is equals to del ID upon del VGS that we need to do. Okay, now mu n cox is some constant. What is your VDS now? What is your VDS? It is 1 minus Vx. 1 minus Vx. So how does it look like for Vx less than 1? So this is Vx, this is Gm, this is 1 volt, right? This is at 0 volt or whatever value we have. Okay, k into 1 we have. So at 1 volt this is something like this. Now talking about the second condition, when Vx is less than 1.2 but greater than equals to 1. So in this, MOS is in linear region again. MOS in linear region, right? Again in linear region. So what is Gm? Some k into VDS. What is VDS in this condition? For second condition, what is VDS? Vx minus 1. Vx minus 1. Vx minus 1 is the VDS. Yeah, so this VDS is fine, but there is one mistake in this one. Del ID upon del VGS we are doing, okay. But here our current is in negative direction. That we forgot. The current is in this direction. Your ID is negative of minus Ix, or your Ix is negative of minus ID. Right? So here we will have minus sign as well. Okay, and then this curve will be there. I just made the curve, so it will look like k into Vx minus 1. Again, it will look like k into Vx minus 1 only. And in third condition, Vx greater than 1.2, MOS goes in saturation. And for saturation, what is Gm? Some constant into VGS minus VT. For third condition, what is VGS minus VT? In third condition, what is VGS minus VT? V outside, that is 0.2. So this is the constant. So if we talk about the overall curve, we will come back to this point. Okay, I will explain you. Gm versus Vx. So first it goes something like this, then it's get saturated. Okay, this is 1 volt, this is 1.2 volt, 1.2 volt. Okay, so did you understand this complete analysis? We will revise it once again. Okay, that's a very good question. For Vx less than 1 gets interchanged, the current equation we write, and we get to know the Ix versus Vx curve. Okay, we get to know it's in linear region and the current is in negative direction. So just as we increase the Vx value, our VDS is getting decreased, or current is getting decreased, but the magnitude of current is getting decreased. In positive direction it is getting increased only, but the magnitude of current is getting decreased. So the magnitude of current is getting decreased. Assume here minus 4, so minus 3 minus 2 and then goes to 0. The magnitude of current is getting decreased, but means it is getting increased in positive direction. Now if Vx is greater than 1 volt, so this is the condition, but for being in linear region we have Vx less than 1.2 volt. Okay, for being in linear region Vx is less than 1.2 volt. So basically we are seeing from 1.2 to 1 to 1.2. So in 1 to 1.2 it goes in linear region. So for linear region, this is the curve we get, and this is Ix versus Vx curve. When we increase the Vx value, or VDS is getting decreased, and because of that your current is getting increased. So it's kind of some low. So this is dependent on square, so it will be some square curve. So this is not linear. Okay, the curve is not linear. Okay, and now when we talk about Vx greater than 1.2, it is simply in saturation region, and the saturation region it is depending on the only the VGS value, and VGS value is constant, so your Ix will be constant. Okay, so that's how your curve will look like. It will go like this and then saturates. Okay, talking about Gm, When Vx is less than 1, MOS is in. When Vx is less than 1, MOS is in linear region, and for linear region, this is the equation we have. So this is the equation we have. So what we are doing is that we need to find delta Ix upon delta Vgs. That we need to find. Okay. So instead of this here, if I write delta Ix upon delta Vgs, that would be equals to minus Gm and this minus alpha. Yeah. So delta Ix upon delta Vgs we need to find, but we know that delta Id upon delta Vgs is some mu n Cux W by L into V overdrive. This is our delta Id upon delta Vgs. If we replace what is Id, Id is equals to minus Ix. For this condition, Id is equals to minus Ix. Right? So like this is this is equals to Gm. Okay. This is equals to Gm, and in bracket I need to write here is delta Id upon delta Vgs is mu n Cux W by L Vds. Okay, this we need to know. So delta Id upon delta Vgs we already know, that is mu n Cux W by L, and your Id is equals to minus Ix. MOS is in linear region and Id equals to minus Ix, right? So if Id is equals to minus Ix, we just wrote here, and then this minus sign will come here. The Gm is defined as delta Ix upon delta Vgs. Okay, delta Ix upon delta Vgs because of this direction of drain current. Okay, Ix is already defined here. Okay, so this is the condition. I hope you have understood the concept here. And for 1.2 to 1, you know Gm would be k into Vx minus 1 because Ix is in this in direction only. And again for Vx greater than 1.2, it would be k dash into Vgs minus Vt. Vgs minus Vt is constant, so it will be constant. So in most of the curve, would like this region will be, this will be linear and this will be saturation. So in most of the curve you will find that simply the if this curve will not be linear, right? Because this is dependent on square value. This is dependent on square value, right? So this is not linear. Like this curve is not linear. The region of operation is linear. This shows the region of operation. Okay, this shows the region of operation. Region of operation. So here the region of operation is linear and saturation, but the curve is not linear and linear. So just taking the linearized form of this one, we get the Gm. Just taking the linearized form, we are getting Gm. Here, if we just take the linearized form of this one, we are getting Gm. Okay. So we'll see more example now. So this was also a very good question. We will see the third question now. Okay. In this one, let me write the question, then we will see it. Hello everyone. Now we will see this question. So again, all the data are same, and you need to do the same analysis. You have to draw Ix versus Vx and Gm versus Vx. So this is the same analysis we need to do. Okay. So again, what you will see here, the VGC is minus 0.9. So the MOSFET will be off. Is it so? No. When Vx is less than 1.9, what will be the MOSFET? MOSFET will look something like this. This is 1 volt. Now this will be drain because this is at higher potential, and this will be source. Current from drain to source. From drain to source outside. Drain to source. So this will be the current. Okay, Id equals to minus Ix. So I have already told you, when we talk about NMOS, higher potential will be at drain and lower potential will be at source. Okay, and this is surely the gate. So what is your VDS here? VDS is 1.9 minus Vx. What is your VGX? It is 1 minus Vx. What is your V overdrive? V overdrive is VGS minus VT. That would be 0.3 minus Vx. Here your VDS is always greater than V overdrive, right? 1.9 minus Vx is always greater than 0.3 minus Vx. Okay, you don't need to think that it is depending on Vx. Take Vx equals to 1 volt. 0.9 will be always, we can't take Vx equals to 1 volt. Take Vx equals to 0.2 volt. 1.7 will be always greater than 0.1, right? It is not depending on Vx. Just simply write what is VDS, 1.9 minus Vx, what is V overdrive, 0.3 minus Vx. Compare it, this Vx will get cut. 1.9 is always greater than 0.3, right? So it will always be in saturation region. What is the current equation in saturation region? Some constant, VGS minus VT means V overdrive whole square. Okay, so I will draw the graph, but what you see here, for Vx greater than 0.3 volt, MOS gets off, right? If Vx equals to 0.3, for Vx greater than 0.3 volt, at 0.3 we are having zero current. So Vx greater than or equals to 0.3 volt, MOSFET gets off, right? Let us assume we are applying Vx equals to 0.4. So your VGS will be 0.6, but your VT is already 0.7, right? You can write VT is equals to 0.7 volt. So your VT is already 0.7 and your VGS is getting equals to 0.6, so your MOSFET is off. Or you can always see is that your V overdrive should always be greater than 0, because VGS should be greater than VT. And what is V overdrive? V overdrive is VGS minus VT. So your V overdrive should always be greater than 0. So when will this be greater than 0? When Vx is less than 0.3. So if Vx is less than 0.3, then only it will be turned on. After Vx greater than 0.3, it will be off. So for 0.3 to 1.9, it will be off. But after 1.9, what will happen? That we will see. So this is the current, and we can draw the curve here. ID versus Vx. ID versus Vx. So it goes something like this, right? This is 0.3. This is 0.3 volt. Okay, at 0.3 volt we will have zero current, and till 1.9 we are having zero current. Now don't, okay, we will draw. No need to draw, but okay, after, before that we just discuss what will be GM. What will be GM? GM will be some constant into VGS minus VT. So what is VGS minus VT? 0.3 into Vx. 0.3 minus Vx. Okay. So we will draw the curve, both curves later on. So let us talk about for Vx greater than 1.9 volt. What will happen? This will be Vx. This will be 1.9. This will be 1 volt, right? This will become, this will be gate only. Now this will become drain, and this will be source. So here your VGS is minus 0.9, that is less than VT. That means MOSFET is O. So MOS remains O. Okay, for Vx greater than 0.3 volt. Okay, greater than or equals to. So we will just draw the final characteristics. Ix versus Vx. Also, yeah, one more thing. In this, talking about this GM, here again minus sign will come, right? That same concept that I told you earlier. Here again minus sign will come. So it will be K into Vx minus 0.3, because your ID is equals to minus Ix. GM is del Ix upon del VGS, and that is equals to del ID upon del VGS minus, right? Look, what is your GM? Del ID del IX upon del VGS. Instead of this, I will write it again. The complete thing. ID is equals to minus IX, or IX is equal ID is equals to minus IX. We can write. Okay. Now, what we know that GM is equals to delta Ix upon delta Vx, right? Ix is equals to minus ID, so we can write delta ID upon delta Vgs with minus sign. We know the formula of delta ID upon delta Vgs, that is some constant k dash into Vgs minus Vt. Now we can write k dash equals to Vgs minus Vt means V overdrive, that is 0.3 minus Vx. That will be equals to k dash into Vx minus 0.3. So now I hope it is all clear to you. Okay. So we will draw the curve now. So after that is remains at 0. So this voltage was 0.3 volt. It remains here, then it goes to 0. This is GM, this is Vx, this is 0.3 volt. Okay, and in this time it was in saturation. Okay, so yeah, that's it. That's the complete analysis. By the previous analysis, you could have done it by your own. Just we need to see that after 0.3 it gets off. Okay, these three questions are on NMOS. Now we will see a question on PMOS. Okay, so let us see that in next video. Hello everyone. Now we will see this question. So in this one we have VTP equals to 0.7 volt, mode of VTP equals to 0.7 volt, and Vx is this. So this time it is and PMOS. So the same analysis will be there. In PMOS, source is at higher potential. Source at higher potential. In case of NMOS, drain at higher potential. Okay. So what do you see? When Vx is less than 1.9 volt, if Vx is less than 1.9 volt, what will happen to the circuit? This is 1 volt. This will become source, right? And this will become drain. Current direction from source to drain. Current direction from source to drain. Source to drain. At the arrow will be always at source. Okay, from source to drain. So yeah, and Ix will be, this will be the current. Okay, so let me write, this is source, this is drain, this is gate, and this is ID, which is equals to minus Ix. Okay, now just write what is VDS, what is VGS. But here we won't write VDS, here we will write VSD. So first write VSG. What is VSG? VSG is 0.9 volt, right? VSG is 0.9 volt. What is VSD? VSD is 1.9 minus Vx. And what is V overdrive? V overdrive is VSG minus mode of VTP. I have told you all the concept related to that. So V overdrive will be VSG minus mode of VTP. That would be 0.2 volt. So here, what is the point? Like, what is the saturation point? Saturation point. So saturation point I can write. Saturation point is 1.9 minus Vx equals to 0.2. That means Vx equals to 1.7 is the saturation point. So when for Vx less than 1.7 volt. So for Vx less than 1.7 volt, VSD is greater than, for Vx less than 1.7 volt, VSD is greater than V overdrive. VSD is greater than V overdrive. that means saturation region. Okay, so we can write current equation. ID will be some constant into VSG. VSG minus VT means V overdrive whole square. Okay, and that means your Ix would be minus K into 0.2 whole square. If we talk about GM, GM would be some constant. Here you can write K dash some constant into V overdrive. But also we will have a negative sign here because of the current in opposite direction. The Ix is taken in this direction, but the current is going in this direction. That's why we have a negative sign. I have already explained this concept. So for drawing the curvature, what we can do is that till 1.7 we can draw something. So it will be something like this. Okay, a constant value, just a constant value. This is Vx, this is Ix, and same for Gm as well. Both values will be negative. Just related to the previous concept, nothing new is there. Okay, this will be Gm, this will be Vx negative till 1.7 volt. Okay, so both will be negative. Okay, now for 1.7 to 1 point, here you can apply a equal sign to 2. So from 1.7 to 1.9 volt. At boundary you don't need to care actually where I am applying, where we actually apply the equal sign at saturation point. Okay, you don't need to worry about that. At boundary point, drain current and that current in linear region or current in saturation both will be the same only. Okay, so for 1.7 volt to 1.9 volt it will be in your VSD would be less than V overdrive, that means it would be triode region. Okay, and current in triode region would be given by I can write Ix, that would be equals to minus K some constant VGS minus VT into VSG minus VT, actually VSG minus VT into VSD 1.9 minus Vx minus VSD square by 2, and this bracket closed. So this is just the equation we wrote, but we just need to see if Vx increases, the VSD value decreases. That means the current decreases. If Vx increases, VSD value decreases. That means the current decreases. Okay. The magnitude of current decreases. So the plot will go something like this. Also, we can discuss about GM. GM would be some constant into VSD, right? Some constant into VSD. VSD is 1.9 minus Vx. 1.9 minus Vx. But a negative sign will also be there because the current is in negative direction. That's why the negative sign will also be there. So, drawing the curve, this we should use for final curve only. This color we should use for final curve only. Here we should use white. So, drawing the curve, this is what we get. This is Ix versus Vx, and this is Gm versus Vx. So the curve will go, first we had some constant, then the current goes to 0 like this at 1.7, 1.9, and this curve goes like this. This is at 1.7, this is at 1.9. Okay, so this was in saturation, this is in linear. Now third condition, for Vx greater than 1.9 volt or equal, you can say. So now your circuit will look something like this. this was 1 volt, I guess. This was 1.9 volt, 1 volt, 1.9 volt Vx Ix. So it will look the same only, right? This is Vx and this is Ix. Yeah. So talking about the equations now, what will be VSD? It would be Vx minus 1.9 volt. Would be VSG? It would be Vx minus 1 volt. What would be V overdrive? V overdrive would be Vx minus 1 minus 0.7. So it would be Vx minus 1.7 volt. Okay, volt you can apply. So here you can see is that VSD is lesser than V overdrive, right? You can see it here because VSD is lesser than V overdrive. How? Because Vx is getting less by more value and Vx is getting less by lesser value here. Let us assume Vx is 20, so it would be, let us assume Vx is 2, so it would be 0.1 and it would be 0.3. So VSD is less than V overdrive. That means it is in linear region. So now we don't need to write the equation, right? Linear region equation we don't need to write. We will just draw the graph now, or we can write as well. Just write the equation. Some constant. Okay. Vsg minus Vt, it is Vx minus 1.7 into Vsd, Vx minus 1.9 minus Vx minus 1.9 whole square by 2. And talking about Gm would be some constant into VSD because this is linear region. What is VSD? Vx minus 1.9. Okay, and this time no negative sign will be there because the current is in the same direction. Okay, now just draw the curve. Now we will draw the final curves. So yeah, in this one, till this point we have explained it. Now if Vx goes high, your VSD goes high, that means your current increases, right? And this is the curve for GM that you can also plot. So this is Ix versus Vx, right? So first it was completely constant, then after that it was always increasing over linear mode. So this point was 1.7 volt. After that, after 1.9 volt, you are having this increasing current. Okay, and in this one we can simply draw it something like this. This is 1.7. This is Gm versus Vx. 1.7 volt, 1.9 volt. Okay, so this is the curve. So I hope you have understood the concept now. Now in any kind of circuit you can draw the curve, and most of the time there is probability that these circuits only will be discussed. No new circuit you will get to see, these circuits only you will get to see. So that's how you analyze the circuit. You can think of any other circuit as well and then you can analyze. Okay, now we will see some other kind of question where you have to draw V0 versus V. Okay, then we will see some capacitor connected questions. Okay, so all kind of possible question we will discuss. So these are very good question and no other sources are available for these kind of questions. So now you are understanding the concepts, I guess. Okay, thank you. Hello everyone. Now we will see this question where you have to plot V0 versus V in now. Okay, so the transfer characteristic you need to plot V0 versus V in. Okay, so your V in is varying from 0 to 3 volt and VT you can take 0.7. So just try to analyze the circuit in that way only. So let us assume like this is drain, this is gate and this is source, that you know. Okay, gate, drain, source. Let us assume there is some current flowing. The current will flow from drain to source. Okay, so drain to source. This current will flow in this resistor. The current will flow in this direction, right? This will develop here positive charge. This will develop here negative charge. If this is 0, this will be some negative value. If this is some negative value, this is plus 1 volt. So is that possible? Right? Not possible. 1 volt, we are assuming we applied some V in, because we have applied V in equals to 1.5 volt. Assume we have applied V in equals to 1.5 volt directly. So can this work in this way? If we applied 1.5, there will be some current flow. If there is some current flow, this is 0, this has to be negative. If the drain becomes negative and source is constant at 1 volt, the source voltage is constant at 1 volt. So will that ever be a drain voltage? Will that be a drain voltage? This won't be a drain voltage. So the drain and source changes its position. Like this doesn't sound correct technically very well, but we can write it. Changes its position. So the upper one is the source now, and the lower one is the drain. So this is the drain now. This is gate. Here we have V in. Then this output. So current direction from drain to source. From drain to source. Okay. And this is the scene we have. Okay. So this is the circuit. Or we can draw it in a better manner to understand it. So I can draw it something like this. Right? This is the same circuit only. 1 volt and from drain to source. So now this works fine, right? This is drain, this is source, and this is gate. Now one thing you need to remember is that till the time when there is zero current, okay, there is, let us assume there is some zero current in the circuit, in the MOSFET. When there is a current flow, uh, like we can see the characteristics ID versus VGS. Over ID versus VDS. So these will be used as well. So I am already drawing it. ID versus VDS. So if we are going from off state to on state, so whenever we are going from off state to on state, there, just as we go to the on state, there is a very minute amount of current flow. So the point here is that in MOSFET, the current will not increase all of a sudden. Like you are having zero current and suddenly you will have 5 ampere current. You will have a very minute current. Okay. So if we consider this one, we for MOSFET, why am I writing like this? Yeah, now it is right. For MOSFET to turn on, VGS should be greater than VT. What is your VGS? V in minus V naught should be greater than 0.7. But whenever MOSFET turns on, ID will be very small. Right? If ID is very small, V naught will be very small. Initially we are talking, okay? not always, initially. So V naught will be very small, that can be equated to 0. Okay, so for V in greater than 0.7, MOSFET turns on. Okay, just above 0.7, not at 0.7, at 0.7 or just above 0.7, 0.7001, it will turn on. MOSFET turns on. Okay, just above 0.7, MOSFET turns on. Now here, what is your VGS? V in minus V naught. What is your VDS? 1 minus V naught. What is your V overdrive? VGS minus VT. V in minus V naught minus 0.7. Here V naught is at source, so it will never define the region of operation. Did you understand this point? V naught is at source, so it will never define the region of operation. Why so? For saturation condition, what is the condition? VDS is greater than VGS minus VT. We can also write it like VD minus VS is greater than VG minus VS is greater than like this. Just I wrote VDS equals to VD minus VS. So VD will be equals to equal sign also there. VD equals to VD will be equal. VD should be greater than VG minus VT. So source never defines the region of operation. Okay, source voltage will never define the region of operation. So you don't need to worry about the value of V naught now. Okay, there is one more thing we will see about the value of V naught. So first thing is that you don't need to worry about the value of V naught. Now we are taking this condition. What is VG? VG, like what is VD? VD is 1 and VG is V in. VD is 1 and VG is V in. So for saturation, 1 should be greater than V in minus 0.7. So V in should be less than 1.7. So for saturation, for 0.7 to 1.7, it will work in saturation region. So what is your ID? ID would be some constant value into VGS minus VT. VGS minus VT, V overdrive whole square. V in minus V naught minus, like if the source doesn't even if the source doesn't even take place in defining the region of operation, then why do we write VGS always? Because like many times student pick VGS from here only. Okay, if you don't write VGS, if you don't just write VG minus VT, you will put in the equation, in this equation, in the drain current equation, you will put V in minus 0.7. You will forget the source voltage. It happens with me as well. मैं भी बहुत बार सीधा अगर VG minus VT से करता हूँ, if I do with VG minus VT, I will simply put V in minus 0.7 sometimes. So that's why we write VGS in all the expression. At least me. That's why I write VGS in all the expression, so that I don't miss this one. Okay, this same ID is equals to V naught by R, R1 or R, right? The same ID is equals to V naught by R, right? V naught by R, this same current is flowing here. This is ID, or capital ID I should write. This is ID. Okay, V naught by R. So from here what you can conclude is that V naught is some constant V in minus V naught minus 0.7. Okay, so if you need to draw this is V out, this is V in. So till 0.7 MOSFET doesn't turn on, MOSFET turns on for V in greater than 0.7. That means for V in less than 0.7, ID is 0. That means V naught is 0 volt. Okay, so this remains at 4 V in 0.7. So after that it goes in saturation region, so the current increases, but the current will not increase linearly. Okay, it will increase lesser than linearly. Like how do I, like, by by this much amount current will not increase. Why? You are increasing v in, you say that your VGS will increase, you are increasing V in, your VGS will increase, so the current will increase. That's why your output will also increase. You are increasing V in, your current increases, because of that your output increases. So if the output increases, your VGS goes low as well, right? So V in will, like, V in will increase more and V naught will increase less. Okay, because I have told you the current doesn't increase so much rapidly. So V in will always increase more and V naught will increase less. So VGS will always increase, but it will not increase very much high. Okay, do you understand this point? If V in increases, you say the current increases. If the current increases, the drop across the resistance will increase. So V naught also increases. So now what is VGS? VGS is V in minus V naught. So your VGS doesn't increase that much. V in also increases, V naught also increases. But V in increases for 2 volt, then V naught will increase for 1 volt. So the overall current will be increased, but not a lot of current. So this kind of curve will not be there. The curve will be a bit lower. Okay. So no one will ask you the curve will be lower. They will just ask you the region of operation. The region of operation is something like this. The curve goes something like this. Okay. You can't solve these equations, right? Okay. Solving these equations will be very tough. So this is the condition. And for V in greater than 1.7, for V in greater than 1.7 volt, we will have linear region. So you can write the current equation, that V will be equals to V naught by R, something constant, into VGS minus VT, V in minus V naught minus 0.7, into VDS minus VDS square by 2. Okay, so your V naught will be some constant, and this again you don't need to write. Okay, now if you draw the curve, so if V in increases, the current will again increase, because the gate voltage increases. If the gate voltage increases, then the current increases, right? We know that if the gate voltage increases, the current increases. So before it was 0, now it goes like this and goes like this. This was 1.7 volt. This was V in. Okay, and this is V out. Now what did I do here? Why does the output voltage saturates 1 volt? Because the output cannot go above 1 volt. Okay, the output cannot go above 1 volt. Why so? Let's see here. In this circuit we can see, yeah, okay, in this, if this goes up to 1.1 volt, what will happen? I will draw a different circuit again. Above 1 volt. Y. This was your V in, this was your 1 volt, and this is your V out. If it goes above 1 volt, 1.1, okay, this here we have R. If this goes above 1.1 volt, let us assume it goes to 1.1. What will happen? It will become drain and it will become source. Current direction from drain to source. Current direction from drain to source. Here we will have positive, here we will have negative. If this is 0, this has to be negative, and that's not possible. First, we are saying that it goes above 1.1 volt. Okay, it goes above 1 volt. Let us assume it goes to 1.1 volt. If it goes to 1.1 volt, this will become drain. This will become source. The current direction has to flow from drain to source. If the current goes in this direction, we see that here V naught has to be negative. So it is not possible for the drain to go above 1 volt. For the V naught to go above 1 volt. Okay. So the maximum value it can obtain is 1 volt. At what value it will obtain, that we can't say, but the maximum value that V naught can obtain is 1 volt only. Did you understand this concept completely? I hope you did. Okay, so we will see more question like that in next videos. Okay, thank you. Hello everyone. So this is the second question. So in this question you have to do the same analysis. V naught versus V in you need to plot, and your V in varies from 0 to 3 volt. Okay. So in this question, the same condition that we saw earlier. What was that? If there is some current flow, if there is some current flow like this, this will develop some negative voltage, right? If there is some current flow from drain to source, if we assume this is drain and this is source, so there will be some current flow from drain to source, and this will have to go to negative. So this potential has to go to negative. So being drained to this terminal is not possible. So what will happen? It will just readjust. So drain and source interchanges. Okay, so what happens is that this is 2 volt, this becomes V in, and this interchanges. Okay, this is R1, this is V naught. This is drain, this is gate, sorry, this is not drain, this is source, this is gate, and this is drain. Okay, and the current ID is flowing something like this. Okay, now we have to do the analysis. So what is VDS? V in minus V naught. What is VGS? 2 minus V naught. What is V overdrive? 1.3 minus V naught. Okay, so like yeah, this is the condition. At V in equals to 0, will the MOSFET turn on? Yeah, so it will surely turn on. Just above V in, it will turn on. Let us assume we have V in equals to 0.1 volt. If V in is equals to 0.1 volt, we have. Okay, so V in will always be greater than V naught. That you also know. In the previous analysis, I have explained why V in is greater than V naught. That I have already explained. Because if V naught goes high, it will become drain, then it will become source. The current has to flow through R1, and then V naught goes to negative. So that V naught has to be lesser than V in. So V in will always be greater than V naught. So just above, if V in is 0.1, let us assume V in is 0.2, so V naught will be 0.1. Okay, here your VGS will be 1.9, your VDS will be 0.1. Understood? So the current will flow. So just above V in, the current will flow. just above V in we will have some V naught. Let us assume we have V in is equals to 0.0001. Then let us assume your V naught goes to 0.00001. That will be a tough calculation for me. Let us assume it goes to 0.005. Okay, and this is this. Then what will happen? What will be your VDS? Your VDS will be 0.00005, right? So this can turn on the MOSFET. And what will be your VGS? VGS will be around 2 volt only. So that is greater than VT, and VDS is also greater than 0. So it will turn on the MOSFET. So just above V in, the MOSFET will be turned on. Okay. So for V in greater than 0, MOSFET turns on. And what is the saturation point here? VDS should be greater than V overdrive. So for this one we have saturation region, and for V in less than 1.3 we have linear region. Okay, so let's check. For V in less than 1.3 volt we have linear region. So let us write the current equation. Some k constant, VGS minus VT. Yeah, from here we can write 1.3 minus V naught, 1.3 minus V naught into VDS, V in minus V naught, minus V in minus V naught whole square by 2, right? ID you can write as V naught by R. So this I can write as V naught by R equals to ID. So basically your V naught is dependent on the V in, that you know here. Your V naught is dependent on the V in. You just don't need to draw the curve by this equation, because you can't really draw the curve by this equation. You just need to think, if V in increases, your VDS will increase, because V in is always greater than V naught. So if V in increases, if drain voltage increases, the current will increase. So if drain voltage increases, the current will increase. Okay, so basically your current increases. This is V out and this is V in. Like if the current increases, that means V naught increases simply. Okay, so if V in increases, the V naught will increase. Okay, but this V naught will increase surely lesser than V in, right? Like if V in increases by 2 volt, the V naught will increase by 1 volt only. Okay, so effectively your VDS increases. Effectively your VDS increases. Surely the current increases. Okay, so effectively your VDS increases, and because of that your current increases. Okay, the concept is not that if drain voltage is increasing, then there has to be the current increasing. This is not the concept. If drain voltage is increasing, drain voltage is V in, V in has to be greater than V naught. If V in is increasing, V naught will also increase, but lesser than V in. Okay, why V naught is increasing? Because the current is increasing. So effectively your VDS is increasing, that's why your current is increasing. Okay, so for 1.3, so many people don't believe in writing the equations, and they, what do? They directly see that yeah, now after that if I furthermore increase, then current will also increase, and then V naught will increase. So they will just draw the graph increasing V naught at saturation, like at after 1.3 they will draw the graph, but we will see what happens. For V in greater than 1.3 volt, it is always advisable to write the current equations. So what will be your ID? That would be V naught by R. That would be some constant, VGS minus VT. V overdrive 1.3 minus 0. 1.3 minus V naught. What do you see here? Your V naught is independent of the input voltage. Your V naught is independent of the input voltage. So how will the curve look like? First it increases, then it stabilizes because it doesn't depend on the input. With increasing input, V naught has this certain value. This is a fixed value. Okay. So this is 1.3 volt. Okay. And this value will surely be lesser than V in. This value will surely be lesser than V in. So this is the analysis. Okay. I hope you understood it. So is there anything I can tell you in this? Yeah, you can think about it intuitively as well. Look, if your V naught is increasing, okay, so your VGS is getting decreased and V in is getting increased with more rate. So your VDS is increasing, right? Your VDS is increasing, your VGS is decreasing. So you are moving towards saturation. If in such, if you are moving towards saturation, if you are going to the saturation, now the current has been saturated, okay, but the current is depending on the V naught value as well, okay, and V naught is dependent on the current. V naught is ID into R. This is basically the same analysis that we have done. So this is what V naught is, and then we show that the V naught is also a constant value. So this is by this analysis only you will tell. Okay, there is nothing like intuition. This is just the intuition that if VDS is increasing, VGS is getting, you are moving towards the saturation, and then at saturation the output becomes the constant. Okay, because the current should be constant, but that is depending on the V naught, and V naught is depending on the current. So output has to saturate. Okay, thank you. Hello everyone. Now we will see this question. In this question again, V naught versus V in we need to plot, and mode of VTP is given to be 0.7 volts. Okay. So now tell me, in this question, will the source and drain will be interchanged? This is PMOS. In this question, will it be interchanged? No. Let us assume like here this is source, this is gate, and this is drain. Let us assume these are interchanged. So what will be the current direction? This one. If this is the current direction, this will be a drop. So source will go to negative voltage. If they are interchanged, the source will go to negative voltage, and that is not possible in case of PMOS. So they are not changed. So if I tell you one simple thing, that is that from the voltage source, whatever the voltage V in we have applied, from there the current should come in. From V in to current should go, from V in current should go to V out. That's it. In the previous problem, here the current V from V in, the current was coming into V in. If we consider this one, but when we reconstructed, when we interchange drain and source, we saw that the current from V in is going to V out. That's it. This is what it means. So from V in to V out it should go. Both V in and V out can increase, but V in will increase more and V out will increase less. Okay. Always V in will increase more and V out will increase lesser than V naught. Sorry, V out will always increase lesser than V in. Okay. So let's start this one. So what is your Vs here? VSG. What is your VSG? That is V in minus 1 volt. What is your VSD? V in minus V out. What is your V overdrive? That is V in minus VSG minus mode of VTP. That means 0.7. So it would be minus 1.7 volt. Okay. First thing is for MOSFET to turn on. Your VO drive should be greater than 0, right? Or your VSG should be greater than, or your VSG should be, or your VSG should be greater than mode of VTP. That means V in should be greater than 1.7 volt. So that means for V in less than or equals to 1.7 volt, MOSFET is off. MOSFET is off. That means V output is 0 volts. Okay. Now we will see this. We have to copy, I guess. This we will copy again. Now we need to find point of saturation. So VSG should be greater than or equals to VSD minus VT. What is VSG? V in minus 1. So we will see that later on. First, what we will see. After V in is greater than 1.7, whenever V in is 1.8, just assume V in is 1.8. When V in is greater than 1.7 volt. If V in is greater than 1.7 volt, this MOSFET turns on. MOS turns on. Okay, but we have seen the transfer characteristics. Whenever the MOS turns on, just as it turns on, the or we can, what we can write here is that instead of this arrow, I will write V in equals to 1.7 plus 1. Okay, so just as the MOSFET turns on, there will be very small current, right? If there is very small current, the V out will be very small. MOS just turns on, very small ID, that means very small V naught, that can be equated to 0 volts. Okay, so at this point your VDS will be equals to, sorry, not VDS, your VSD will be equals to, almost equals to V in, your VO drive, that is VSG minus VT, V in minus 1 minus 0.7, so it would be V in minus 1.7. So here your VSD is greater than VO drive, that means it is in saturation region. Okay, so after that the saturation region comes. Okay, so just as we turn on the device, just as we turn on PMOS or NMOS, just as we turn on, and if it is in this kind of configuration, or in case of NMOS, if it is in this kind of configuration, it will never go into linear region, it will always go into the saturation region only. Okay, you need to remember it. Just as we turn on, never assume it in linear region, it will go into saturation only, because there will be very small amount of current, and if there is very small amount of current, then there will be very small amount of V naught, and by this we saw that it will go into saturation. Now when will it come into, when will the MOS switch the region, or when will it come to triode region? Okay, so what is the condition? VSD should be less than VSG minus VT. That means, what is VSD? V in minus V naught, should mode of VTP. VSG, what is VSG? V in minus 1 minus minus VTP, that is 0.7. So V naught should be greater than 1.7. So what does it say? Here your V naught also comes in action. Your V naught is also a matter of concern here. Why so? Because it is actually in the previous questions what we saw is that if we are if we were calculating this condition, not this one, for saturation and linear, the V naught was always at source. Okay, so it was getting cut. Getting cut means it was not coming into the action because Vd is greater than Vg minus Vt. Okay, so it was not coming into the action. Now it is at drain. So now it is coming into the action. Your VSD. So whenever the V naught is coming into the action, now it is a very good problem. So for being into the saturation, what is your condition? Your V in is greater than 1.7 volt, right? And your V naught is less than 1.7 volt. Okay, your V in is greater than 1.7 volt. So your V naught will not suddenly go to 1.7, right? It will take time. So this is the scene, V naught and V in. Look, if your V in increases, this is in saturation region, and for saturation region we can write the current equation, some constant into V overdrive. V overdrive is this one, V in minus 1.7 volt, V in minus 1.7 square. So if V in increases, the current increases. If the current increases, then V naught increases. Also, I have to remove this one. This is ID is equals to V naught by R. So your V naught would become some constant into V in minus 1.7 whole square. So if V in increases, then your V naught also increases, but at a slower rate than V in, right? Let us assume this is 1.7, this is 1.7 volt, this is V naught and V in. Okay, now this goes on increasing. This is the linear region. The V in your V, it is increasing like this. At some point it will reach, at some V in, at some V in you will have V naught equals to, at some V in you will have V naught equals to 1.7 volt. At 1.7 volt you have V naught equals to 0 volt. After at 1.8 you will have some V naught. After 1.9 you will have some V naught. At some V in, this voltage of V in, let us call it VA. At V in equals to VA, you will have V naught equals to 1.7 volt. So for V in greater than VA and V naught greater than 1.7, it goes into linear region. Did you understand this? Look, first what we did, we saw that initially it is not turned on, it is in cutoff region, so there is no point of analyzing, the current is 0. Now then what we saw, just as V in goes very 1.7 volt, just above 1.7 volt, the MOSFET goes into the saturation region, not in triode region. Now we checked when does it goes to the linear region. So we saw the condition that when V naught goes above 1.7 volt, if V naught goes above 1.7 volt, then only it goes to saturation region. Okay, sorry, if V naught goes above 1.7 volt, then only it goes to the linear region. Okay, so if we draw the curve like for saturation region like this, okay, then we saw that at some V in potential, V naught goes above 1.7 volt. So after V in is greater than VA and V naught is VA, this is VA, okay, and V naught is greater than 1.7 volt, then we goes to the linear region. In linear region, what will be the current? Some constant VGS minus VT. I have become very tired. VGS minus VT into VSD, that is equals to V in, VSG minus VT actually, minus V in square by 2. Actually, from here only you can see that. Is there something? No, 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 no. V in minus V naught it is. That's why I was thinking what is happening. V in minus V naught minus V in minus V naught whole square by 2. Right, I am doing it right now. VSD minus. Yeah. So this is the current equation. Now you need to see if the current will increase or decrease. So if you increase the V in, your V naught will increase, right? But not as much as, what do we say? But not as much as V in. Okay. If you increase V in, V naught will increase, but V in will increase more, V naught will increase less. So effectively your VSD will increase, and your your VSD will increase, and your VSG will also increase, because your V in is increasing, so your VSG is also increasing. So your VSG is increasing, and effectively your VSD is also increasing. So the current will increase only, right? So the current will increase. Okay, it will keep on increasing like this. Curve goes like something like this. Okay, so do you understand it? Look, it's not that simple. You need to have good concentration, okay, and good concepts as well. And these kind of questions are not asked to everyone. These are very good conceptual question, okay. And if you are asked these kind of question and you answer them like this, then you are surely selected 100%, 101% selected. If they don't even have vacancy, then also you will be selected, okay. So just see the analysis that the way I am doing, okay. It's just a simple stuff, you know everything, you just need to analyze in this way, and just keep on revising these circuits, okay. Then you will understand everything, and you can also find the value of that VA. Here only I have drawn the complete circuit. Actually, I should draw it again. Okay, I will do it. I will draw it again. So till then you will try to find the value of VA. This VA. This VA. Just put you have this equation. Just put VA here. You will get the value of, no, sorry. Just put V in equals to VA. You will get V naught equals to 1.7. Just put it here, and then you can find the value of VA. So finding VA at V in equals to VA, we have V naught equals to 1.7 volt. So 1.7 volt will be equals to K dash into VA minus 1.7 whole square. So VA would be equals to 1.7 by K dash under root plus 1.7. So that would be VA. Okay. So this is VA, and let me draw the curve. Yeah. So what will happen is that it will increase after that. Why so? Because your effective VSD is increasing and your VSG is also increasing. So the current will increase. So the curve goes like this. So these are the 7 questions we have studied till now. So revise them once again. Just draw the curve in your rough notebook. Just think about them and just do the analysis. Okay. Now we'll see few more questions. Okay.